Today's presentation, I'll be discussing a case study related to CITGO's site-specific benzene fenceline monitoring plan for US EPA Method 325. This case study uses our microscale VOC analyzer or micro gas chromatograph. And the microscale gas chromatograph that's mentioned in today's presentation is manufactured by Omniscient, who is headquartered in San Jose, California, and Apex Instruments is the exclusive distributor for this product line. For today's presentation, I'll start by sharing a brief overview of EPA Method 325 for folks who might not be familiar with VOC fenceline monitoring. Then I'll discuss the motivation for needing continuous VOC monitoring using our micro gas chromatograph. Then I'll get into the details related to CITGO's site-specific management plan and how they went about utilizing real-time monitoring equipment to comply with Method 325. And finally, I'll share some outcomes from this SSMP case study. I'll share some comments from CITGO's environmental management team, and I'll discuss a bit more about our VOC analyzer at the end. So first, the scope of this presentation really pertains to fenceline monitoring provisions under Title 40, Part 63, and specifically we'll be discussing benzene monitoring using EPA Method 325 at CITGO's West Plant in Corpus Christi, Texas. So briefly covering what is US EPA Method 325. So Method 325 for volatile organic compounds from fugitive and area sources is broken into two portions. In the first portion, 325A, it discusses sample deployment and VOC sample preparation. So it describes how to collect VOCs from inside facilities or from fugitive/area emission sources using passive diffusive tube samplers. And the image, the schematic on the right, shows a passive sampler in a sheltered weather hood. These passive samplers collect VOCs that passively adsorb onto sorbent materials within the tube and collect VOCs over 14 days. 325A also describes where to place these passive samplers when you deploy them at a facility, as far as how many to deploy and where to space them depending on the size and shape of the facility. And it also has guidances for collecting meteorological data. In Method 325B, the sampler preparation and analysis portion, the method describes procedures for preparation, conditioning, blanking, and shipping of sorbent tubes before sample collection. It describes the lab analysis required of these passive samplers and typically describes the process of thermally desorbing the VOCs from the passive sampler using gas chromatography for separation and then mass spectrometry for detection. So this is the lab analysis piece. So just to quickly summarize the full Method 325, passive sampler tubes are deployed on site at specified locations. They're passively collecting VOCs for 14 days, at which point they're recollected and transported to a laboratory for analysis, typically by thermal desorption, gas chromatography, and then mass spectrometry. And a full cycle of testing, you'll get your results from the passive sampler tubes about 21 days after they were initially deployed. And note that the regulation states that the annual average delta concentration value cannot exceed 9 micrograms per meter cubed or 2.8 parts per billion volume. If an exceedance occurs, corrective action is then needed. And I know the title slide mentions a site-specific management plan, so I wanted to just touch on what that is briefly. So an SSMP for short is a formal plan that a facility must develop and get approved by either EPA or a delegated state agency when compliance requires site-tailored procedures. So this often occurs when a standard method approach has shortcomings for a specific site, and there needs to be a tailored approach for that site to be able to test successfully or regain compliance status. Okay, so now that we've covered a little bit of the regulatory space pertaining to this case study, I'll discuss what motivated CITGO to develop and implement their SSMP. So CITGO's West Plant Refinery is situated along the banks of the Port of Corpus Christi in Texas. And this port is known for its heavy industrial activity. So I actually had the chance to visit this port last fall and got a tour up and down the port and saw the numerous petrochemical facilities, refineries, storage tanks, asphalt manufacturers, all types of activities going on in this site. The port handles the shipping of liquid bulk, dry bulk, general cargo, and all other types of special cargo equipment. And this facility, the facilities here, the activities, the ships, they all contribute to the presence of VOCs in the local airshed. So we have a very crowded industrial site where CITGO is located. Additionally, the CITGO West Plant Refinery has several process units, including a coker, hydrotreaters, storage tanks, boilers, and more. And this site is subject to regulation under Title 40, Part 63, and has been measuring VOCs via Method 325 using passive sampler tubes since the regulation existed. Between August 2022 and August 2023, this site experienced benzene annual average delta concentration exceedances greater than the action level, which they suspected was related to off-site upwind contributions, so from their near neighbors. And these exceedances demonstrated the need for corrective action. Now, when you zoom in on CITGO's West Plant, so this is shown as the shaded yellow region on this Google Map screenshot, it's probably not surprising that CITGO was picking up benzene contributions from their neighbors. CITGO's nearest neighbors include other refineries, gas plants, asphalt manufacturers, storage terminals, and refinery docks. And when they were looking at the historical wind speed and direction data, CITGO could identify upwind benzene contributions were skewing their benzene delta C values. And they suspected that this was leading to the exceedances on multiple occasions, which demonstrated the need for corrective action. However, you can see that due to this lack of separation between facility sites, I mean, these facilities are separated by maybe a fence, or definitely a fence, and maybe a small road. They're right on top of each other. It's very hard to implement corrective action for upwind benzene sources outside of the refinery boundary. So this is what led CITGO to develop this SSMP. All right, getting into what this SSMP details. So basically, CITGO needed a strategy to acquire real-time benzene monitoring data in addition to weather data or wind data, and use it to correct for these 14-day passive sampler measurements that were including the off-site upwind sources or the benzene from their neighbors. They needed to be able to calculate benzene from the neighboring facilities and essentially subtract it from their passive sampler tube data to show that they were in compliance. To do this, CITGO continued to conduct their standard passive benzene sampling following Method 325, and they also deployed automatic gas chromatographs into the field to provide continuous real-time benzene measurements. CITGO at the time decided to use two different automatic gas chromatographs. They used our Omni 2000 series micro GC pictured here in the blue, and they also used NMET's EGC. And they would position these auto GCs at locations around their fence line where they suspected to have the highest possible risk of benzene exceedances from their neighboring facilities. So this map here is from CITGO's SSMP and shows the locations where benzene sampling was conducted. Again, the shaded yellow region is CITGO's facility, and the pink shaded area is representing the neighboring facilities that they suspected of being offsite upwind benzene source contributors. Each of the dots on this map represents a site where Fenceline passive sampler monitoring was being done for benzene monitoring. And these locations monitor both on-site benzene and off-site benzene. So there is no ability to differentiate initially where the benzene was coming from in those calculations. Now, the blue dots on this map signify where the gas chromatographs were co-located with these passive sampler tubes. So CITGO then from this initial map, CITGO would add or relocate auto GCs to monitor different locations where they found unusual benzene concentrations or upwind, or where wind patterns were recorded to be pulling off-site benzene onto their facility. I'll also just note that the benzene data points that were recorded when the wind originates from angles that are within these blue shaded areas correlate to basically off-site upwind benzene calculations. And so when wind was coming from those upwind directions, they would record the auto GC data and use that data to offset the passive sampler tube calculations. So, and to determine how and when to move the auto GCs around to different locations, they used some additional equipment. So they were also using a handheld VOC sensor type device and an optical gas imaging camera to scan for fugitive emissions from around the fence line. So when they would find a higher area for benzene, they would relocate the auto GCs to this location. And I wanted to just take this opportunity to highlight an important distinction here is that when you're monitoring in the field environment, it's important often to utilize multiple different technological approaches. I often talk to folks who are looking for like a silver bullet, and there is no single instrument that can do it all and fits all of your constraints. So it's very important to remember that each technology inherently has advantages and shortcomings. But to achieve a specific goal, you have to select the right combination of appropriate tools and technologies. And I think CITGO does a really good job in this SSMP of doing that. Of course, they're using the passive sampler tubes that are super reliable and generate highly accurate data from the laboratory analysis, but they have no or very poor time resolution, and they're functionally consumables. Then as needed imaging or sensing devices provide a more portable option for them, and they're flexible to use, but the data accuracy doesn't necessarily match an analytical instrument. And then the use of the continuous monitoring auto GCs provides very accurate data and good time resolution, but their performance won't match that of a laboratory grade GCMS for analysis. But each piece of equipment in this SSMP case study really provides important information for its specific use. So I like to just highlight, pick the right tool for the right job. Okay, and switching back over to the SSMP, this is the light math portion of the talk. It shows how CITGO was actually calculating the benzene concentration. So the first thing they had to do was to calculate the corrected benzene fenceline concentration. To do that, they were calculating the near field source contributing concentration. So this first value here has to do with values generated from the auto GCs. So this involved determining the average of the benzene concentrations measured when the wind direction was from upwind offsite sources, and then multiplying that by the number of benzene measurements when the wind direction was from upwind offsite sources in a 14-day period, and dividing that by the total number of possible benzene measurements over that same 14-day period. So then FS value is used in the next calculation, which is to calculate the corrected benzene fenceline concentration. So the near field source contributing concentration from the auto GCs and the uniform background benzene concentrations are subtracted from the benzene fenceline concentration, or the value obtained from the passive sampler tubes. And then CITGO reports either the standard passive sampler tube value or the corrected result with an explanation that the auto GCs were used in the correction value. And so that pretty much wraps up how CITGO used the auto GCs for their SSMP related to 325. I also just wanted to share some updates since this SSMP was approved in May of 2024. CITGO has been able to demonstrate regulatory compliance by conducting this data reduction calculation process using the auto GC data. CITGO's also purchased additional Omni auto GCs and has expanded their benzene monitoring efforts. And I wanted to just share a little bit of feedback from CITGO's environmental advisor. When asked how they liked the equipment, they said that working with the equipment had been a very smooth process. The units had better uptime and have required less maintenance than other units they use from a similar vendor. And when asked what features they found most useful, they said the functionality of the Omni cloud-based platform, the ability to integrate Omni data with other software they were already using was a very helpful feature of for their monitoring efforts. All right, now switching gears a little bit, I wanted to share a little more information about the Omni 2000 series auto GC, some of the features and functions for folks who might not be as familiar with the technology. So this is a picture of the Omni auto GC out in the field. It's a small box about the size of a shoebox. It weighs about 16 pounds, and it's able to speciate many common VOCs with a limit of detection in the low parts per billion range. You can adjust the sampling time to generate results in just a few minutes. It's able to operate fully off the grid with a solar panel and a battery backup. It does not require any carrier gas, so you don't need to be out there constantly changing gas cylinders. And it requires infrequent calibration, only once about every 6 months, because we're using capacitive detectors, which don't experience much signal drift. The overall unit's pretty low cost, and we also provide an optional C1D2 enclosure or a bump test kit. The cloud-based platform enables continuous monitoring and quick reaction time. So the unit's deployed out in the field. It communicates with the cloud via a web LTE modem, and crew members can monitor operation of the Omni continuously and can react quickly to fix leaks or to investigate other emission events. To show you a little bit how this device works, this is a picture of the underside of the Omni device. There's the sample inlet there. Again, it's pulling just ambient air, so we have a small particulate filter at the front end that prevents any debris from entering into the chamber. We also have mechanisms for removing humidity from the air. Again, we're just using an ambient air as the carrier gas. And this is a picture of the GC on a chip. So it's a little bigger than the size of a penny. This video here will show you how the GC works. So we have a bidirectional pump that initially pulls the analyte across the chip, where the analyte will interact with a pre-concentrator material and collect during the sampling time here. After the allocated sampling time, we heat the pre-concentration material. We heat the pre-concentration material, we reverse the flow of the pump, and the analyte's separated across the column and analyzed by the detector. And I also wanted to show a quick example of a chromatogram generated from this device. So I mentioned briefly we use two capacitive detectors. So if you're familiar with gas chromatography, you'll immediately notice that this chromatogram is weird because it has two different signals. So one of the detectors is registering positive capacitance. The other is able to report both positive and negative capacitance. And so this gives us three parameters for quantifying VOCs. We have the standard retention time lending to chemical identification and peak height corresponding to concentration. But then we also have a third parameter, which is the peak height ratio. So it's basically the difference in capacitance between the two detectors. And that helps to further identify chemical species, which is helpful when there's co-elution of chemical species. We're able to figure out which chemical it is based on the polarity of the sample. Our GC can detect other aromatics, halogenated hydrocarbons, and alkanes, and it has generally a detection range from low parts per billion to about 6 parts per million. So with that, I hope you enjoyed a little bit of the interesting case study that CITGO used our AutoGC and other technologies to generate real-time continuous monitoring of benzene data to help offset their benzene calculations from outside sources. CITGO is able to regain compliance and has been expanding their benzene monitoring using the AutoGCs. And here's a picture of one of our devices with its C1D2 enclosure. And with that, I'd like to open it up to questions.